the rest of the week. So I'm going to talk about quantum Gibbs sampling, a topic close to my heart, and that we are also doing in the Toucan project, a project that also involves Michal, who is also around. And as we're in Brazil, I thought I should use our Toucan also as some sort of mascot throughout the talk. And for the Brazilians and the audience, even though I'm from São Paulo, this has no political connotations. Okay. So I think I would even be as bold as saying that we had some sort of revolution in the last few years when it comes to quantum Gibbs sampling. And this was kickstarted by the work of Chen and others, because they were able to write down a Lindbladian that is provably quasi-local. You can efficiently implement it on a quantum computer, and you can also prove that it converges to a Gibbs state you want to maybe prepare on your quantum computer. And previous to their work, or before their work, we didn't have any example of a Lindbladian that satisfied all of these requirements at the same time. And I think it's fair to say that we had been looking for something like this for quite a long time. And after they sort of found this very nice construction, a lot of work followed showing that these Lindbladians can actually efficiently prepare various families of quantum states that maybe not necessarily what I would advocate you should do on a quantum computer, but at least we were able to tick some boxes regarding states you would actually expect to be able to prepare efficiently on a quantum computer. Say, for instance, high temperature Gibbs states or perturbations of product states, free perturbations of free fermions, or also 1D Gibbs states at any fixed temperature. And again, I don't think these are sort of the things you would necessarily want to do on a quantum computer. I see it more as some sort of sanity check that we have found sort of the right way to quantize methods like Markov chain Monte Carlo, which are very successful both in theory and in practice to prepare interesting states of classical systems. And hopefully we will also be able to use these methods to prepare non-trivial quantum states or quantum many-body states on quantum computers. And I think it's an important sanity check to make sure that if you propose some method, then you can also show that in the regimes where you expect things to be easy, it indeed prepares things efficiently. So this is all good news. I'm really excited by that. But there are also some bad news, right? So the algorithms of Chen and others, they really need a full-fledged, large-scale, fault-tolerant quantum computer, because they need block encodings and non-trivial ones. So this is not something you'll be able to implement in the near term. This is really like a long-term algorithm. Okay, so even though we are not even though we are preparing, let's say, 1D quantum states or something like this, which aren't the most complex objects, they would, running this version of the algorithm still would require a fancy quantum computer. However, there is this nice work by Ding and collaborators that developed a repeated interaction approximation of this Gibbs sampling algorithm by Chen and collaborators. So essentially, they're mimicking some formalization process on a quantum computer, and it is a very simple sort of algorithm, and it provably converges to the quantum Gibbs state you'd care about. And all you need to do is you sort of you have your system you want to formalize, and at each step you make it interact with, you make one qubit that comes in at some thermal state that depends on the Gibbs state you actually want to prepare. And you make it talk to your qubits. Then the next qubit comes in, talks to your qubits. I'll explain in a few slides what are the actual interactions you implement. But sort of the setup is very simple. So this is definitely something you could imagine implementing in the near term, right? You just like, one qubit comes in, you do some Hamiltonian simulation, next qubit comes in, Hamiltonian simulation, and so on. So sort of the number of auxiliary systems you have to implement is sort of more or less under control if this process converges rapidly. And the primitives are also sort of not kind of near-term friendly, namely Hamiltonian evolution. So that's essentially what they showed, that sort of with this sort of process, which again is much friendlier than the Chen result, you can actually also get quantum algorithms that provably converge to a quantum Gibbs state you might care about. So this is great news. However, it is in principle unclear how often you have to repeat this process, okay? So what Ding and others showed is that if you, in the limit of infinitely many interactions with this qubit that comes in and interacts with your system, you will indeed converge to this Gibbs state you care about. But the question, of course, is how many times do I need to repeat this before I actually get a good approximation, right? Because in practice, we don't want to run this process for infinitely long time. This would, of course, be a useless algorithm. We want to run it a small number of steps and then know that we prepared some interesting Gibbs state. And this is sort of related to the question of mixing times, okay? So whenever you have we want to prepare some sort of Gibbs state, let's say with classical Markov chains as well, there's always this question of how long do I have to run this process for before I converge to this distribution I want to sample from, or in this case, this quantum many-body state I wish to prepare, okay? And what our work is about is to show that whenever Chen's construction is efficient, okay, in the sense that it will converge in polynomial time to the quantum Gibbs state you want to prepare, then this significantly simpler setup where you have these qubits coming in will also be efficient, okay? So this is sort of the main message, that sort of whenever the fancy algorithm works well, the simpler algorithm will work too. And in fact, the Chen's algorithm, it is fancier in the sense that you need more complicated things on a quantum computer, but it is simpler to analyze. So from, let's say, an implementation perspective, the Chen algorithm is the fancy one, but from an analytical perspective, this repeated interaction one is the more difficult. So so this thing here, like this Chen construction, is very nice for pen and paper calculations, and sort of we are transferring results from this setup to this setup that is a bit more difficult. So because we know that Chen's algorithm can prepare a variety of quantum many-body states efficiently, we immediately also get that we can sort of, in this very simple setup of one qubit flying in, Hamiltonian simulation, another qubit flies in, Hamiltonian simulation, we can also prepare a variety of states provably efficiently. So again, 1D, perturbations of product, refermions, this is all efficient. And again, I just want to stress that I'm not claiming that this is what you want to do with your quantum computer. These states, most of them, you can also simulate efficiently on classical computer, so you have maybe some small polynomial advantages, is just sort of more evidence that these quantum algorithms can actually prepare non-trivial quantum many-body states. And just to be a bit provocative so that we maybe have something to discuss at the pool on Wednesday, I would like to compare the state of affairs here for these methods to, for instance, variational quantum algorithms, where like we had like maybe 12 years of research on them and now 3 years on Gibbs states, and we can provably show a larger sort of families of states that we can prepare with them. So I think there's more. There are many reasons to be optimistic about the potential of these methods. Okay, so maybe just to be a bit more precise about how these algorithms actually work. So as I mentioned before, at each step, you have one qubit flying in, and it will be just at this formal state of just the Pauli Z Hamiltonian. The temperature beta and is fixed by the temperature you want to reach with your for your quantum many-body Gibbs state. And then, but there's this other parameter omega, which you're going to choose at random. And at each step, you're going to implement some Hamiltonian on the system, which is going to be the Hamiltonian you want to formalize to. You're going to implement some Hamiltonian on the BAF. That doesn't matter too much. I mean, again, it's just like a 1 qubit, right? And then you have to implement some sort of interaction between the system and the BAF. And it's going to be like a random interaction at each step. And it's going to couple just one qubit of the system with your BAF, which you're going to choose at random as well. So you have to do Hamiltonian simulation on the whole system with the Hamiltonian you want to formalize to, but the system BAF is also only a 1 qubit coupling, which is time dependent as well. So again, this is not a very complicated setup to actually implement on your quantum computer, at least in my opinion. Yeah, and then sort of we keep repeating this thing many times, and it's going to define you some sort of quantum channel that is given as follows, right? So you're just going to implement this time evolution for a certain time t with your initial BAF system, which you're going to then discard. So the question is sort of how long does it take, or how many times do I have to repeat this process before I actually converge to the Gibbs state I wish to sample from. Yeah, so what I just said. And well, you might be asking yourself, okay, but what is so cool about these new constructions? Don't we know already like how to describe formalization in quantum systems? Don't we have the Davis generator? And the Davis generator, it has some nice properties. It satisfies detailed balance, and it has this maybe a bit daunting representation. But the issue is somehow twofold. Okay, so to derive this sort of Davis equation, you need to assume that the Bohr frequencies, that is the differences of eigenvalues of your Hamiltonian, is small compared to the coupling to the BAF. But this can be an exponentially small number. Okay, so the coupling to the BAF has to be very, very, very weak. Okay, so if your coupling with the BAF is very weak, then you also expect it will take some sort of long, for this approximation to hold, you would also expect that the formalization time will also be very slow, and this is not something you want in your algorithm. You want to converge to the Gibbs state as fast as possible. Another thing we dislike about the Davis generator is the fact that if you look at the jump operators that define it, you can write it like this, like some sort of operator Fourier transform. And if you have non-commuting systems, these guys are going to be supported everywhere. on the system. They're not going to be local, not even quasi-local, and this makes sort of their analysis very very difficult from a theoretical perspective. So we want things to be quasi-local at the very least. So maybe your jump operators on your system, they're not completely constrained to a few qubits, but they have some sort of decaying tail as you move away from some qubits you're interacting with. And well, so this is why these Davis generators are not so easy to analyze and implement on a quantum computer. And but this is sort of friendlier. And just to give you some more details, as I mentioned, the only sort of thing you have to change at every step is you not only have this qubit flying in, but you also have to implement this time-dependent Hamiltonian between the system and the bath, and the time dependence is going to be given by this Gaussian envelope and some time t. And as you see, there is this extra parameter here. There are two parameters that we need to pay attention to. The first one is this alpha, okay? And this alpha dictates how strongly my system is interacting with my bath. Okay, so this is something we need to be careful with. The other thing we need to be careful with is this kappa thing, this kappa parameter over here, which of course is going to determine the width of this envelope. So these algorithms, they come with these two extra parameters, which are the kappa and the alpha. Now, once we've picked those parameters, we also have to determine for how long we're going to let the qubits talk to our system. Okay, this is this parameter large T. So putting it all together, at the end of the day, we're implementing this sort of random quantum channel here, which is, again, running this evolution from time minus t to t, the system BAF1, and with our initial state. And this unitary evolution has these parameters alpha and kappa. And it is this channel phi here that we need to analyze to understand how fast we converge to a given Gibbs state. All right. So this slide is starting to get more technical, but let me just quickly run you through it. What one can show, and this is not our work, this is work by Ding and the others, they already show this, is that in some limit, you can actually approximate this quantum channel here by some Limbladian, okay? So, composed with some unitary channel, and this is just the unitary you have on your system, okay? So in particular, if your system is already at the Gibbs state, like evolving it by this unitary will not change anything, right? Because they commute. So in some sense, if we understand how well this Limbladian over here works, or how fast applying this Limbladian converges us to a Gibbs state we care about, then we're also able to understand how often we need to apply this channel over here, because, well, they sort of approximate each other. But again, there are these parameters alpha and kappa looming around, and they determine how good this approximation is. And this Limbladian here has a very has a lot of structure, and in particular, it looks a lot like the families of Limbladians I mentioned before that stem from the work of Chen and others. Okay, and these are Limbladians we're learning to control well. So we already have some sort of theory and understanding of of how fast these Lindbladians formalize. So sort of the hope would be that you can transfer the knowledge we gained in the last few years about these guys to these guys. Okay. Now I have a slide that should just, you're welcome to ignore it. The only thing you're not welcome to ignore is the fact that we have this 1 over kappa over here, okay? What are these formulas saying? So the formula, remember what I just told you, that these Chen, the Lindbladians by Chen, we understand quite well. Okay, so we would like to transfer the knowledge we have about those systems to these repeated interaction systems. And this slide is telling you that if you compare the Lindbladian we get from the repeated interaction to this thing over here, which is essentially a rescaled version of the Chen Lindbladian, well, I actually, the other offer is Gillen. I guess I used Gillen here, so that's why the G. So sorry about it, not being consistent with first offers. But the point is that this guy is something we now know how to control well and understand well. And this is the thing we would like to understand well. And it's telling us that we need to make kappa large for this approximation to be good. But making kappa large is related to sort of how this Gaussian envelope will look like. And kappa large means that this Gaussian envelope will become wider. And this is something we don't like, okay? Because if you look at the jump operators on this Lindbladian over here, which is the Chen one, the larger the value of kappa, the less quasi-local they become. Okay, and we like quasi-local evolutions because they are easier to analyze. Okay, locality is very useful when you're doing these proofs. What is the big sort of issue over here is that to get a good approximation, we need kappa large, but once we get a good approximation, we are not in the regime where things are actually easy to analyze. So our main, so just again to draw this point, again, if you pick kappa of order 1, then everybody is quasi-local. We know how to analyze it. To get a good approximation, we need kappa large. So there's the sort of conflict there. And our main contribution, so this is sort of for the experts, is just a way of bridging these two regimes. So again, on one side, we have this kappa of order 1. Everything is quasi-local. We like it. We know how to analyze it. On the other hand, we have this kappa large regime where the repeated interaction systems are well approximated by the Lindbladians, but then they're not quasi-local anymore. So there are these two regimes, and they don't really, in principle, don't really talk to each other. But our main, oh, this didn't render correctly. Doesn't matter. The main point is that we are able to show some sort of monotonicity of the spectral gap. So if you know something about mixing times, you know that sort of the spectral gap of the Lindbladian is one of the key quantities to analyze how fast you converge. And we were able to show that the mixing time for this kappa equals of order 1 is a lower bound on the kappa large regime. So in some sense, if you can prove that the quasi-local evolution converges rapidly, it's efficient, then also this other regime, which is when these repeated interaction systems come into play, are also going to be efficient. So in some sense, whenever the quasi-local time evolution by Chen works well, also this repeated interaction thing will work well. Okay, and that's how we transfer all the results we had for Lindbladians to these simpler systems. And this comes from some nice representation of the so-called Dirichlet form in terms of convolutions. Okay, so maybe for the interest of time, I'll just skip this. And just to show you sort of the sort of result we get. So for instance, we show that if we are in the regime where you perturb some product state, so some non-interacting Hamiltonian, then the number of times you need to apply this process to converge up to epsilon to your favorite Gibbs state is going to scale like this. So n to the 10 epsilon minus 4. I'll talk about this in a second. And maybe 2 weeks ago, these two authors used our techniques to further get a quadratic improvement in epsilon and shade off some ends here. So yeah, so they already, like, we put this out 2 weeks later, they already use our techniques to slightly improve it. Now, okay, so our toucan tried to mix something, and we did get a cake. We did get the result, but like the toucan, maybe you're a bit disappointed, right? Because let's be honest, like I told you, like, oh, maybe near term it's nice and blah blah blah. But this is really bad, right? N to the 10 epsilon minus 4. Let's be honest about it. These exponents are terrible, right? But I don't think that's the end of the story. Okay, so I think this is just an artifact of our analysis, and that's the first analysis in this direction. So I believe that we can significantly improve all of these steps if we further localize the underlying proofs. And another thing that makes this convergence very slow is the fact that each time step, we only make the system interact with one qubit. So there's like a limited amount of entropy you can get out of your system if you do that, right? So if you maybe made it interact with more qubits or designed the interaction in a smarter way, you could speed things up much faster. You could formalize things faster. Another thing that would be interesting to prove things about, or maybe also look at numerically, is how noise resilient these processes are. So there are some results about dissipative processes being a bit more resilient to noise than unitary dynamics. And last but not least, more large-scale numerics to see how far we can push this. Like maybe I'm being too optimistic, and actually a high-degree polynomial is indeed required to ensure convergence. And that's just life. But I'm still optimistic. And again, these systems are pretty simple. It's just one qubit coming in and Hamiltonian simulation. So maybe one could also play with these algorithms in the lab. And with that, I'd like to thank you all for your attention, and also thank my co-authors. It's always fun to work with these people. And yeah, that was it. Thanks.
Thanks for your very nice talk. You wrote as one of the open questions about the size of the bed.
Yes.
And how are you modeling this bed? It looked for me it is like some sort of collision model, right?
Yes, yes. So in physics, people, I guess, call it these like collision models. It's exactly like that. Yeah. So it's very simple. So yeah, maybe here I already have it. So it's indeed just like one qubit coming in at it, and it only you pick one of the qubits of your system at random, and then you make it interact with that guy. So that's it. I don't think it would be particularly hard. I just think one would have to redo their derivation and also sort of design it in a way that is a bit smarter, so that you get more entropy out at every step. I don't think it's like something really that requires fundamentally new ideas, but it would be nice to do it. Yeah. Mm-hmm. Thanks. Mm-hmm. That's an interesting question I didn't really think about before. So sort of just for the audience, the question is like at each step you need to pick your qubit at random, and you also sort of have to pick the state your ancilla is in at random. If one could de-randomize it, yeah, yeah.
Like we have this older work where, for example, we randomize two grids where you approximate channels where something
Hmm.
there, Anthony and Pascal group. And if you make a longer sequence of just unit errors, it goes into approximate.
Yeah, I think that's a very cool idea. Maybe another thing we were thinking a bit about, which goes in the same direction, is sort of if you're close to mix, then somehow maybe you can also just reuse the qubits you've so that you don't have to keep generating fresh ones. So also getting fresh randomness like that. So yeah, I think those approaches are also quite promising. I'd be happy to discuss more about it. Thanks.